What's up, players, gangsters, OGs? It's your boy Slick Vic from Slick Vic Codes. I don't have an intro, but I do love hot moms, and today we are starting the first episode in our Before You Take Data Structures and Algorithms Watch This series. We got some good content coming for you today. We're going to talk about big O, little o, big omega, big theta, the formal definitions, the tightnesses of the bounds, of course little omega as well. So stay tuned for the content, and I'll see you guys after my workout.
Yo, what's up, guys? So we have the whiteboard with it, and we got the formal definition of big O with us. So without further ado, let's get right into it. A function f of n is big O of g of n if f of n is greater than c times g of n for all n greater than n naught. Okay, so a bunch of jargon here. Let's break it down, right? So what is f of n and what is g of n? Okay, so f of n and g of n are just functions. Okay, so just like in math class, you have f of x, you have g of x, right? They're just functions. They're functions of n, right? So saying that f of n is equal to n, right? This is the same saying y equal to x or f of x equal to x. Okay, it's the same graph, same function, right? Same meaning. All right. Now, what about the constants c and n naught, right? So c is just a scalar for the function g of n. It's all it is. Always apply to g of n. No application to f of n. Okay. Now, n naught, right? This is the final place where f of n and g of n cross. Okay. So once they cross that, they never cross again, right? Now, notice the restrictions. You have c must be greater than 0, n naught must be greater than or equal to 0. Okay. So I'll give you here a bit of an illustrative example. Let's say f of n is equal to n, and g of n is equal to n squared, right? So we only care about positive values, right? So we only care about this first quadrant, right? And let's go ahead and draw them. So this could be our g of n, right? And this is potentially our f of n, okay? Right? So notice this is where they cross, okay? They never cross again, right? So this is our n naught, right? Now, suppose you're looking at this function, right? Right? I know it's a dirty example here, right? But this is the last time they cross, okay? So this would be the n naught of this function. All right, now getting back to our original example, right, with f of n of g of n, f of n equals n, g of n equals n squared, okay? So you see past this n naught point, they never cross again, okay? You see that f of n is less than g of n for all n greater than n naught. So with that being said, by definition, f of n is big O of g of n, okay? However, you might be saying, oh, Slick, what about this c value here, okay? So c gets applied to this g of n term. Well, okay, notice, right, there is no value of c that makes n squared grow slower than n for all values of n, right? At some point, it will cross. So all the c does is change this value of n naught, changes where it's going to cross in the graph, right? So it may end up making the parabola or the x squared go like this. It may make it go like this, right? These are all just different scalars on this g of n function. But regardless, right, it still crosses and it just changes where that value of n naught will be, okay? So with that being said, f of n is big O of g of n. It's big O of c times g of n, right? And the way we would write this notation here, okay, right, is we would say that n big O of n squared. Notice this is our f of n right here, and this is our g of n right here. Okay, it's just some functions, we're just plugging them in. Now, I'm gonna go ahead and bring you over to Desmos, get some more functions, and get you a better visual so you can understand better. I'll see you guys in a second.
All right, yo, so we at Desmos, and we got some functions. So let's go over it. So we have this example here. And what do you know? F of n is in fact big O of g of n, because I did happen to make this example. But let's get into why. So as you see, if I can get my mouse, past this point right here, right, this f of n function is always increasing. They're always of less value than this g of n function, right, which is n squared. Now, this point right here is called n naught. Right, this is where it happens. This is where the beauty, the magic happens right here. It's the last time they cross, right? So potentially, right, the function maybe like crosses like 6 times, right, and then gets to some point and they don't cross again, right? So that last point is the n naught, right? So now you can't forget about the c though, right? So c is a scalar, and I did have it. Oh, we're gonna add slider. Okay, so c is 1, so nothing happened. But check it. When we change c, right, this value changes, right? So all c does, right? Remember, c can never be negative, right? And it can't be 0, right? So all c does is changes this value of n naught, right? That's all it does, right? In this example, f of n is big O of g of n, right? So n is big O of n squared, right? By that same concept, g of n squared is big omega of f of n, which is n, right? So you'll see the big omega symbol. It's just like the reverse concept, right? So past some point, right, n will always be less than n squared, and therefore n is what we call the lower bound, right? So big omega is associated with the lower bound, whereas big O is associated with the upper bound. Okay, now, so one thing we've established, right, is that f of n equals n, right, is big O of g of n squared, right? But also, and something you'll probably see come up in your classes, is the fact that n is also big O of n cubed. Okay, right? Because here's the point, right? This is n naught in the case, right? Put any scalar here, any value c, right? And it just changes the n naught, right? Same principle, right? Same principle type of thing. Can't be negative, right? Can't be 0. So f of n is big O of n cubed as well, right? Now, additionally, it's also big O of 2 to the n, big O of n factorial, right? All sorts. And here's a good example where it crosses twice. Okay, so note, this point right here is the n naught term. Okay, not this point here. This point does not matter, right? This point matters. The last point where they cross. Okay. Now, with that being said, these different functions, as they differ in while they are all big O's, right, and they are all upper bounds, they differ in their tightness of the bound, right? So, for example, when comparing n squared and n cubed, right? So look, they both have the same n naught, right? They both cross for the last time in the same point. But as you can see, the n squared term is always closer to the n term, right? To the term we're looking at, right? The function for all values of n, right? It's always closer. So we consider this to be tighter, right? The tighter bound than n cubed. So that's what the tightness of a bound means, right? Now, additionally, this n cubed term, right, is big omega of n squared and big omega of n, right? Because for all values of n past this n naught, they grow, their values are less, right? We would also say that n cubed, right, is a tighter big omega to n squared than n cubed does with n, right? So n is technically, right, so n cubed is technically big omega of n, but it's a tighter bound with n squared, right? So same kind of concept. Now, the last element that you'll have of the bigs is, in fact, the theta. That's right, the angle. Okay, so what you need to do is you take these functions, right, and you have to find, you want to take the cosine over, so it's actually the arc cosine, right, because you have to take the inverse trig, right, No, I'm just kidding, guys. So theta is when you have big O and big omega of the same term, right? So if you have a function and it is big O of n squared, right? And that same function is also big omega of n squared, then that function is big theta of n squared, right? Simple as that. So in terms of the bounds, we say, big O is the upper bound, right? Big omega is the lower bound, and big theta is like the average case, okay? Or often actually it's the exact case, right? So with big O, you would say, okay, this algorithm will take no more than this many steps. Big omega says, okay, the algorithm will take at least this many steps, and big theta says the algorithm will take exactly this many steps. And often when you use stuff like the master's theorem, you actually solve for the big theta. Now, there's one more terminology that you may come across, or probably will come across in your data structures course, and that is the little o and the little omega. They're not used often. Really, I haven't used them outside of this course, but all they refer to is when you have bounds that are not very tight, right? So you could say, n cubed is little o, or excuse me, n is little o of n cubed, right? Because it's not really a tight bound. So the only practical case I could see for this is if you're saying, okay, I have this algorithm here. I haven't proved that it's n squared yet, but I do think it is big O of n squared. But I can guarantee it's at least big O of n cubed. So I'm going to say right now that it's little o of n cubed to indicate that it might be better. The only practical case I could see for it, it's really, you don't use it often, or really ever, but it may come up in your class, so I figured at least I'd cover it.
Alright guys, before we end the video, I just want to give you one last piece of advice for your actual data structures course, and that is to memorize this expression right here, okay? So what is this? This is just an expression of showing what functions are greater than each other, right? So, C is always going to be this constant time, by the way. You may see this represented as O of 1 or big omega is 1. These are common representations of constant time, but even if it's like big O of 1,000 or 1,000,000, it doesn't matter. It doesn't grow with the size of n, and therefore it is always smaller than the rest of these functions. Okay, it's always smaller than everything. It's always the smallest. Constant time is the smallest. It is the big O of everything. Okay. With that being said, log n is less than log squared of n, which is less than root n. Okay, right? And additionally, right, log n is big O of log squared of n, which is big O of root n, which is big O of n, down and so on and so forth, all the way down the expression here. Okay, now I can guarantee you for sure 100% you will be quizzed on this. Okay, not necessarily just this expression, but the big O questions, right? And let me tell you something, guys, those big O questions, free points, easy points. Know this by the back of your hand. Write this down several times. Those should be free grabs, free points, okay? But every semester people get that stuff wrong, right? I can almost guarantee that this is some of the easy stuff you're gonna be doing all semester, guys. You don't wanna lose points on your first test over dumb stuff like big O, right? So memorize this like the back of your hand, write it down 20 times if you have to. I probably wrote this down 5 times a day, and then I would write it down again as tests would come up just in case, okay? Now, one other helpful advice about this, people get confused with log n and root n, okay? So just know the difference between these two, look at the functions in Desmos, write those two specifically down. A couple irregulars, right, is n log squared of n. I did happen to see this on one of my tests, so I did include it. Another irregular, it might be n factorial to the power of n factorial, right? So just know these, just know those irregulars. And yeah, guys, with that being said, I'm gonna end the video here. Next video should be on big O reductions and the master's theorem. So I hope to see you guys over there.